Can you go back?
Anyway, start wherever you want.
See you.
All right, it's done.
May not use it.
Okay, good morning, everyone. So today we want to start the second part of this lecture, which is coding for computing. So far, we saw the role of coding for caching, and now we want to switch to computing and see how coding can help us do computing. And this part, I will cover three, topics, very short. These are all of them are very recent results. One of them is to use coding to improve coded map reduce framework. The other one is to use coding to deal with stragglers. And the last one is to use coding for like communication-aware coded computation. Okay, so the first one is coded map reduce. I told you at the in the first day that we know how to do computing, we know how to do communication, but then they interact. This problem is solved. So we don't know how to deal with this interaction very well. And so our target is to come up with some trade-off between communication and computation. And of course, this problem is an old problem. It attracted researchers' attention from very early on. And people, for example, ask, what is the minimum communication load to do a specific computation? And I can mention two seminal papers, one of them from CS community by Yahoo, and the other one from information theory community by Corner and Martin. So in this paper, the question was how to calculate a specific function demonstrated in this table. The other one is how to calculate XOR of two bits, two sequence of bits. However, if you search around, what we are doing right now is in the CS, data companies, you would see a little yellow elephant with the name Hadoop. This is the framework that they use in the daily basis in data companies. And so motivated by this framework, Hadoop MapReduce, we formulate a problem like this. So in this formulation, we have n input files, W1 to Wn, and we want to calculate Q functions out of these n inputs. So the functions are phi1 to phi-q. And the computing resources that we have are K servers, which are connected to a shared link. We assume that these functions, these Q functions, it can be linear, nonlinear, anything, can be decomposed into as two sets of functions, some inner functions and an outer function. So each function is equal to concatenation of these two. the inner function, each inner function works on each file separately, and then an outer function combines all the results together. So let me show you on a picture of what's going on. Let's say you have 6 inputs, W1 to W6. Okay? Then you have, and you want to calculate 3 functions, phi1, phi2, and phi3. From now on, I call them blue function, green function, and red function. So the inner functions here process each file separately. For example, here the vector function G1 processes W1 and generates 3 data, okay, 3 outputs. We call it intermediate values. One of these are useful to calculate the blue function. The other one is useful to calculate the green function. The other one is useful to calculate the red function. Okay? So we process each file separately, generate 3 results. Each of them is useful for one of them. Okay? Another way to say it is that we are compressing this file, okay, such that the result is useful for, I generate 3 intermediate values. Each of them is useful to calculate one of these functions. Again, we have another inner function, processing W2, generate 3 intermediate values, and so on and so forth. Now, when you want to calculate the blue function here, we need to pass all blue boxes through an outer box, which is F1. This is the outer function. And then calculate phi1. We calculate phi2, we pass all green boxes through an outer function, generate phi2, and so on. Okay, so the first point is that any function can be decomposed like that. Why? At most, we can use identity function here, and phi1, phi2, phi3 here. This is the worst thing that you can do. But so any function can be decomposed like this. The second thing is that this kind of decomposition is very suitable for parallel processing. Why? As you see here, first we have one round of processing without any communication. They call it mapping. Okay? So in this round, we just process each file locally without any communication. We have a communication phase to exchange this intermediate value, which is called shuffling. And then we have another round of processing, which is called reducing. Okay? The fact that we are separating processing from communication is very helpful to speed up the computation. Otherwise, when you are doing processing, you are waiting for some results to do the computation. It will slow down the speed of computation. This is why they like this framework. And on top of that, it's easy to implement. So now, how we decompose functions, for different jobs, you have to do these decompositions differently. And there are some courses on how to do this decomposition. For any specific job, there are some best ways to do this. For example, as far as I remember, Harvard, Harvard, there is a course on that, how to fit a specific task to this framework. Okay, now how to implement this over a set of processors? We do it like this. First, we assign each server some of the files to map. Okay? For example, here we give server 1 file 1 and 2 to map, and it creates intermediate values for the first file and intermediate values for the second file. Similarly, here we give the file 3 and 4 to second server to create intermediate values for file 3 and 4, and so on. Then we assign each of the server one of the functions to reduce. For example, here we give the job of reducing the blue functions to server 1. And clearly, we have to move all the blue boxes to server 1 to be able to reduce the blue function. Okay? Of course, some of them is locally available here, but we need to move the rest of it. Okay? So framework like Spark allows us to store some part of the data. Okay? So this is keeping part of the data for the next round of processing is allowed in reality. Then, for example, for the green function, we assign it to the second server, move the green boxes here, do the calculation here, and so on. So this is how we, implement parallel processing using the MapReduce framework. The other point is that we can assign each file to more than one server to process. For example, here we can assign file 1 also to server 3 to map, or function input 2, file 2 to server 2, or file 4 to server 3. Why do we do that? One reason is to reduce the communication load. Okay. And there is another reason for that, which is they want to have some fault tolerance. Sometimes they repeat the job to have fault tolerance. Okay. Now here we can define the communication computation trade-off as follows. First, we need to define computation load. The computation load is defined as the total number of mapping that we are doing. Okay? So remember, in our example, we had 6 inputs, so they had to do 6 mapping. But here, because I repeated some of the mapping, here I have 12 mapping. Okay? So the total number of mapping that we are doing here is 12. This is called computation load. Okay? And to make it clean, we normalize it by the minimum number of mapping that we need. So here we need to do at least 6 mapping. So we normalize the total number of mapping by 6. And we call it computation load. Normalized computation, and clearly this is a number greater than or equal to 1. Then we define communication load as the number of intermediate values that we need to move around in this link. And again, to make it clean, we normalize it by the total number of intermediate values that we generate.
Why is the reduced part of the computation load?
Why they are not.
In the metric, why aren't you measuring the reduced computation?
So here, good question. In this part, we assume that the reduce, we're just doing it once, okay? And so it is not, it's just constantly eliminated. But if you want to, another version of the problem is to have several rounds of this, and then you may want to reduce each function, each file, in function in several places because you want to do it in the next round. Then you have to consider that. But here in the very first framework, you don't consider that. You can consider that. Now, and we define computation trade-off as this. So what is the minimum number of, what is the minimum communication load for a specific computation load? And the design parameters are map assignments and communication scheme that we use in this. Okay. So to get the game, let us go through the example that I explained before. 3 servers, 6 files, 3 reduce functions, and this assignment. Okay. So in this case, you can see that if you want to reduce the blue function here, you have to move all the blue boxes here, but part of it is locally available. You don't need to do it. And here again, if you want to reduce the green function here, part of it is locally available. You don't need to move it as here. Okay? So you need to move the rest of them. Okay? So you need to move the shadow boxes here. So here, for example, the communication load would be 12. The total was 18, so it is 12 by 18. And in general, you can see that formula for that, if you don't repeat any input, would be something like this: 1 minus 1 over e. This is the trade-off. This is the minimum communication load if you don't repeat the computation. Now, the question is if we can reduce the communication load by increasing the cost of computation. And yes, we can do it. Let's see how we can do it. So here I assign each file to 2 servers to do the mapping. So here, file 1, I map it here, and here, file 2, I map it here and here, and so on. Okay? Therefore, the computation load here is 2, twice as many. And so here, each server calculates the intermediate values for each of these functions, for each of these inputs. And now to reduce their function here, you know, this part is already available. You need to give it the rest of it. Blue 5 and blue 6 is not here. You need to give the server to be able to reduce it. Again, here, that part is already here. Here, that part is already here. Therefore, we need to deliver the rest of it, deliver the remaining part to each server. So here, for example, the communication load will be 6, normalize it by 18, with V1 over 2. And in general, if you have R times computation load here, the communication load would be 1 minus R over K. So if you have the curve of communication load versus computation load, the trade-off would be something like this. So if you have R time, if you increase the computation load by R, the communication load will be reduced by K minus 1 divided by K minus 1. This is a very bad thing, right? Why? Because if the system is large, this is approximately 1. So it says that if you just increase the computation load like this, it's not helpful. Okay? So it's not going to give us anything for large systems. So the question would be, can we do better than this? And in particular, can we have a scheme that gives us a non-vanishing gain for large K? So if the system is very large, we don't lose the gain here. And the answer is this. What we can do using coding, we can achieve a curve like this, where communication load and communication load are, inversely proportional. Okay. So computation load times communication load are the multiplication of these two is almost 1. Okay. And the good thing here is that it doesn't matter how large the system is. Okay. This gain does not vanish. And how do we do it? Let me explain by an example. So the same placement that we had here, map assignment. Remember, we need to give green 1 to this guy and red 3 to this guy. We need to give blue 5 to this guy and red 4 to this guy, and we need to give green 5 to this guy and green 2 to this guy and blue 6 to this guy. Okay. Remember, we needed to send these 6 boxes. But using coding, we can have some saving. Why? Because green 1 that we want to deliver to this guy wants to deliver green 1 to this server, but green 1 is already available here, and this guy needs to deliver red 3 to this guy, but this red 3 is already available here. So if you send the XOR of these two, it's useful for both of them. Again, here, blue 5 that you want to give it to this guy is available here. Red 4 that you want to give it to this guy is available here. So if you send the XOR of these two, okay, both of them can recover what they want. And the same for the other one. So by this coding, when we increase the computation load by 2, we can reduce the communication load by 2. So factor of 2 increasing in the computation load, we have factor of 2 improvement in the communication load. Okay? And so we achieve this formula. Okay? So in the general scheme is like this. We have n files, and we want to increase the computation load by R. We divide these n files into k choose R batches of files, and we assign each batch to a specific group, a specific subset of n of k servers. And then using based on, if you do that, we have the coding operations that I explained. So as you see, the scheme that I explained is very connected to the caching scheme that I explained the other day, with one problem. Okay. The problem is this one. You know, in caching, in caching problem, in the placement phase, we didn't know what each user wants. And it was very important for us. When we were filling these caches, we didn't know if this user will ask for the glue file. Otherwise, the solution was very easy. But in the map reduce problem, we know who will reduce each function. Okay? And this one actually stops us for a long time, waited us for a long time, because we didn't know how to handle this case. But the way that we resolve it is this one. When you are doing map reduce, when a server is mapping a file, it has to create all the intermediate values. And the reason is like the file is available at the server, and like creating intermediate values is like compression. And so we want to do this compression before communicating. Okay? So this is why they presume that when you are mapping an input, you are creating all intermediate values for all the outputs. This scheme is optimum. Okay, we cannot do better than this, and the reason is that to prove the outer bound, first we prove an inequality like this, which is based on like some, like some information theoretic equality at each node. Okay. So I don't go through this, but to see the game in reality, we implemented this scheme for on Amazon EC2. And the job that we consider was terasort. Terasort is a kind of sorting that is heavy in communication. So, you see some numbers if you want to implement it for a data size of 12 gig. And as you can see, the time for shuffling for communication is dominant, time taken. Okay. So the time for mapping, or unpack, reducing, and all of this is very small compared to the shuffling time. And so this is a good problem to see if we can increase the computation load and reduce the communication load. So we did it using the coded map reduce framework that I explained by increasing for example, the computation load by 2. And we saw that the communication time is divided by 2. When you increase it by 2, you can see that the shuffling time is reduced by 3. And then the overall timing will be less than before by a factor of 3. Okay. So this is the first time. So as said, we can extend this result to multi-round of communication, multi-round of computation. If you have a graph of jobs, you can think about it. Some of them are completely solved, some of them are open. You don't know how to deal with them. For example, if you have a graph of jobs and you want to do this, you have some initial results, but you don't know how to do it optimally. Okay, so this is the first part. I want to move to the second part, which is using coding to deal with stragglers. Do you have any questions?
So, I mean, in practice, would people be interested in that 4x factor?
Of course. You mean for the timing?
Well, I mean, so the reason I'm asking is because, for us, there's no doubt that there's a gain, but when people implement, sometimes they don't even bother until they see 10x, right?
Actually, no. 2 times is a lot of saving. I need to double check with people, but as far as I understand, yes. For example, if a computation takes like 1 day and you make it half a day, it's a big deal, no?
I mean, to me, yes. I've seen several cases where people are like, oh, but there are other hidden costs, and unless they tell them it's 10x, they're like, well.
I tend to believe that it's important. But
no, I would agree.
Yeah, but
have you checked with it?
I need to ask more.
And is it
We presented this one in distributed computing conferences, and they were excited about it. And so first, they liked the fact that the overall time is less. The other thing that they were excited was that we are increasing the computation load by a factor of R, and the computation load is reduced by a factor of R. It's not just subtraction. And for them, it was kind of surprising. Okay. But these are very recent results, all of them. They are still exploring. See what about that. Okay, so now I want to go to the second part. And here I want to see if we can use coding to deal with the stragglers. Okay? And especially we focus on matrix multiplication. You know, why we care about matrix multiplication is that, you know, matrix multiplication is a core operation in big data analysis. So in a lot of this analysis, iterative algorithms, you know, iteratively you have to multiply matrices together. And so if you can reduce the timing for matrix multiplication, you can speed up the overall time of the system. Okay? And so the problem is that often these matrices are huge, okay? Because these matrices are coming from the database and the size of them are big. And so one processor cannot handle these matrix multiplication. So what you need to do, then you need to distribute this computation between different servers. As soon as you distribute the computation, you will have another challenge. The challenge is that some of the servers are slow. Okay? So for example, you distribute your job between 4 processors, and among these 4, one of them is slow. Why? Because it's getting warm, you know, or somebody else put a job on it. For unknown reasons, or various reasons, some of these processors may get slow. Okay? And so you are the overall speed is defined by the slowest server. And the question is, can we deal with it? How can we solve this problem? What is your suggestion? Let's say you have a job, and you divide it into 2 jobs, and you put it on 2 servers, and then you realize that one of the servers is slow. What do you do?
Use one more server.
You use one more server. How?
You code.
You code, okay? So you are familiar with coding, but actually in practice they repeat. They just hire 2 more servers, and they repeat these 2 jobs there. And then if 2 of them, you know, if from the 2 that are doing the same job, if one of them finish, then you can go down. But we know from information theory, communication, that repetition is not a good idea. So we want to see if we can use coding for this operation. Let me give you an example. Let's say you want to multiply this matrix A to vector X, and this matrix is a very fat matrix. And this X is a very tall vector, apparently. Okay. And so you realize that, you know, a server cannot handle it. So what you need to do, you hire 2 servers, and one of them will multiply A0 to X, the other one multiply A1 to X. And the problem is, again, one of the servers is slow, you don't know beforehand, so the overall time will be very high. So how can you resolve this? You can add another row to this matrix, which is A0 plus A1. Okay. And now you can get 3 servers. One of them multiply A0 to X, the other one multiply A1 to X, the other one multiply A0 plus A1 to X. Okay. You can see if any 2 servers finish their job, you're done. For example, if server 1 and server 3 finish their job, you can calculate A times X. Clear? So if you want to multiply a matrix to a vector, what you need to do, you need to use an MDS code the rows of matrix A, use an MDS code of rate K to N, and then if any K of them finish, you can recover the.
So here, I mean, the matrices are going to be constant, and you'll do this many times. Otherwise, just creating those is good.
Yes, exactly. And because you know, usually this represents the database. Okay. Now, how about matrix multiplication? Here I multiply a matrix to a vector, What if I want to multiply a matrix to a matrix? Okay. So let's see what we can do. You know, let's say, for example, you want to multiply this matrix to this matrix. This matrix is fat, this matrix is tall. The processor cannot handle it, so you divide it into 4 jobs. Okay? A0 times B0, A0 times B1, A1 times B0, A1 times B1. And again, you will have problem because one of the servers are slow, so you want to speed up the computation. What can you do? You can code both matrices. Okay? For example, here you can add another row to this matrix, A0 plus A1. Another column to be B0 plus B1. Now you will have 9 multiplications. Yeah? So you get 9 servers. Each of them will do one of these multiplications. Okay? Now I have a question. Can we recover the original result from the result of any 4 servers? So remember, here I have 9 servers to do this multiplication. Okay? And the question is, if I have the result of any 4 servers, can I recover the original result? Where? Well, from here, from this coding. See, the coding would be. Okay. So, if you do it this way, so you have 9 servers. One of them is multiplying A0 to B0, another one A1 to B0, and so on. So you have these 9 servers. The question is, if I have a subset 4 of these results, can I recover the original result, the result of the multiplication? The answer is no. Why? Because look at this tree. For example, let's say you have the result of these 4 servers. Okay? The result of these 4 servers are linearly dependent. Why? Because this one plus this one is this one. Okay? So from these 4, you cannot recover the 4 terms that you need to calculate the product. Okay. See? This one plus this one is exactly this one. So these 4 are not enough. It's not like any subset of 4 servers can give us the result. So the question would be this. Is there any coding that when it goes through matrix multiplication, the result becomes MDS, meaning that from any subset of 4, I can recover the result of the matrix. Okay? This is the question. So this code is not good, because when it goes through multiplication, the result is not MDS. We want the code that when it goes through the operation of one matrix multiplication, the result becomes MDS. The construction that we have is this one. So we define 2 functions, fx and gx. Fx is a0 plus a1x, and gx is b0 plus b1x squared. Okay, for x and a scalar, we define these 2 functions, a0 plus a1x, b0 plus b1x squared. Okay. Now we ask server I to calculate f transpose of fi transpose times gi. Okay. For example, server 1 will multiply a0 plus a1 times b0 plus b1. Server 2 calculates a0 plus 2a1 and the other one b0 plus 4. Okay. Multiply these 2 together. What we claim is that this one is an MDS. From any subset of 4, we can recover the original. Okay. Why? So remember, if you multiply fx to gx, the result would be this. Okay? Just multiply that. So as you can see, the 4 terms that you are looking for are coefficients of different powers of x. Okay? know what is this code. From coding course, you should know it. This is Reed-Solomon. Okay? In Reed-Solomon, when you want to code, you put data as the coefficients of different power of x. Okay? And then when you want to communicate, we send the result of this polynomial for different values of x. Okay? So therefore, in this way, you design a code that if it goes through the matrix multiplication, the result is MDS. So from a subset of any 4, you can recover the result of matrix multiplication. And because it is Reed-Solomon, we know there are good way of decoding. Okay, so this is the second result that I wanted to cover. So you can certainly you can generalize it to like any size of matrices. Any question?
It's a good way of reconstructing the also efficient because you will have to do processing to reconstruct the submatrix.
Exactly, because it is Reed-Solomon, you can rely on all the good way of decoding Reed-Solomon to decode it. So
So if you have two general size matrices, you again get exactly MDS.
yes. So one of them. So for example, let's say you have like 5 rows. One of them you code it by 1x ultimate to x4. The other one is b0 plus b1x5 plus b2x10. You jump the other. This one it jumps by 1. The other one it jumps by 5. When you multiply them together, all the results that you want will be the coefficients of different power of x. And yes, to say something.
Sorry, so if you have 2 square matrices, what do you do?
So it's like this. If you have like 3 blocks here, okay, and you want
Each block has more than 1 entry.
oh, it doesn't matter. That one is okay. So even here, each of these could be a matrix.
Oh, okay.
Okay. That
Oh,
one
I
is-
see. Oh, okay. Now I understand. So these are actually matrices.
Yeah, this could be. It doesn't have to be a row. It's just it can be a matrix. So we can assume that a server can handle this matrix times this matrix, but it cannot handle the entire multiplication.
And what if you wanted to do sort of you wanted each server to do just actually this multiplication of entries, it's really small matrices, not just whole rows. So here you're
Oh, we don't know yet.
you don't know.
We don't know yet.
It's
We're working
possible
on
that
it.
there could be.
I can't imagine. This one was published I think 2 or 3 weeks ago. So now. Okay, we are working on the others and others. Okay.
What is the assumption on the underlying field? Does it work on real number?
For real numbers, yes. So you need to have, if you want to, for example, here, if I want to do it for 9 servers, I need to have 9 distinct values for x. Okay? It has to be greater than or equal to 10. Let me start from you. So this is the size of the field that you need for this Reed-Solomon code. Okay. So this is the second one. You can read the paper here. The third one, we call it communication-aware computing for edge processing. And in this one, the scenario is a little bit different. So let's assume that you have k users, and each of these users have an input, d1 to dk, and they want to calculate phi of d1 to phi of dk. Okay? But they don't have enough processing power to do the job. So what they have to do, they have to offload it to the edge. And at the edge, we have m different edge nodes. So as you can see here, you can have a two-phase solution. In one phase, each edge node has to calculate some functions of the inputs, and then we have a communication phase where the result has to be delivered to the users. And here we assume that these functions are linear. So these files, all of them are the same, and these are linear. So this linearity is important for us here. Okay. And then the question would be, what is the trade-off between computation load at the edge and communication load here? So we define the computation load again as the number of total functions that we calculate at the edge, normalized by k. And then communication load, we define it as the delay that you need to deliver the data. So the delay of delivery, we call it communication. Number of time slots that you need to deliver the data. And so we want to know what is the trade-off between these. So let's see like two examples and see how it goes. So let's assume that, for example, you have two edge nodes and two users, and you have two inputs, D1 and D2, and you want to calculate a linear function of this D1 and D2. Here, for simplicity, I assume that you want to multiply A to D1 and A to D2. But it works for any linear function. So one approach would be to ask edge node 1 to calculate AD1, edge node 2 to calculate AD2, and then now it will be the computation phase. For the communication phase, we ask each of them to deliver these results to the users. Now here, how many times we need? How many times slots we need? This will be an interference channel. We need at least 2 time slots to deliver this result. Okay. So here, the computation load is 1 because each processing, we exactly do 2 processing and we have 2 jobs. So the normalized one is 1. And the communication load is 2 because it takes 2 time slots to deliver the result. Let's go to another extreme. So here we call it minimum computation because we are doing like exactly the computation load that we want. Then we consider another case. Here we ask edge node 1 and edge node 2 to do both of them do both calculations. What is the advantage here? The advantage would be in the delivery time, we can deliver it using zero forcing, and therefore we can send this one simultaneously. Each of them receive what they ask for. So here, the computation load would be 2 because we are doing twice computation as we did. But the communication load would be 1. Okay. So this is minimum communication scheme. But the question that we have is this one: can we achieve these two? Can we achieve minimum computation load and minimum communication load at the same time? Okay. And the answer is yes. And it's not that difficult to do. So the idea would be to, instead of computing each job separately, we compute a coded version of input. Okay? So this is the idea that we want to push. We want to say that instead of calculating each of them separately, first do some computation over the data and then process. How? Like this. So we ask edge node 1 to calculate phi of this. Okay, this linear combination. And edge node 2 to calculate phi of this linear combination. Okay. So which is here, it will be this one and this one. Okay. Then if each of the edge nodes send these two at the same time, this is exactly zero forcing. Okay? So each of them can recover the data that they are looking for. Okay? So as you see, the computation load is 1 because we are doing 2 computations, and the communication load is also 1. So we achieve the minimum computation and communication load at the same time. Okay. So this example says that processing the coded input would be useful if you want to do communication after that. But then we see a challenge here. What is the challenge? The challenge is that in the computation phase, we need to know the channel information. Okay? The combination that we consider depends on the channel information. But you know, channel is usually time varying, and maybe in the computation phase, we don't know the channel information. And the question is, can we achieve the same result without knowing the channel information in the computation phase? Can we come up with a universal scheme that no matter what the channel is, it works and achieves the computation load of 1, computation load of 1? And the answer is yes. No. The solution that we have is this one. So the general result is that we can achieve computation load of 1, computation load of 1, without knowing channel information in a computation phase. The solution is like this. Here we have to expand the solution over several, computations. So we assume that user 1 has two inputs, D11 and D12, and wants to know AD11 and AD12. And user 2 wants to know AD21. User 2 has one input. It's not symmetric, but we can make it symmetric later. Now, here we ask server 1 to calculate AD11 and AD12 plus D21. Server 2 to calculate AD11 plus AD21. The important thing here that you should notice is that this computation is not a function of channel information. Yes? You don't see any of this channel information here. Now, we send these three symbols over 2 times. How? First, we calculate vector V11, V12, and V2 such that V11 and V2 cancel each other at receiver 2 when it goes through the channel, and V12 and V2 cancel each other at receiver 1, at receiver 2. So V12 and V2 cancel each other at receiver 1, V11 and V2 cancel each other at receiver 2. So we choose 3 vectors with this property. There are infinite answers for it, we choose just one. Okay. Now, if we send S11, S12, and S2 using these modulation vectors that we calculated, you can easily see that receiver 1 can recover what it asked for, and receiver 2 can recover what it asked for without any interference. Okay? So here, you have a encoding independent of channel information, and this is this. So we can make the solution symmetric by changing the role of user 1 and 2. But what is the communication load? What is the computation load for this solution? So as you see here, we wanted 3 functions, and the computation that we have is 3. So the computation load is 1. But the communication load is not 2 anymore. It's 4 over 3. It's less than 2. Okay? And if we are ready to expand it over more time slots, we can actually achieve 1. Very surprising. So it is like we have a universal solution for zero forcing, which is kind of independent of the channel information. Okay? So, the idea that we are using here is motivated by another result, a very different, problem, which is communication over interference channel, 2 user interference channel with 2 relay nodes by, by Jafar team. Okay. So there they didn't have universality any of this because the channel information is known, they can use anything. But if you look at the scheme that they have at the relays, a part of the scheme is independent of the channel information. And this is where we selected that part and used it here. Okay, so, and we can do it for more than 2 users. If you have k users, Then we have another version of it, which is called, motivated by K by K by K relay channels. The scheme is called allowing network diagonalization. Again, without knowing it, they had some universal zero forcing solution. So we can use it and achieve the same, again, minimum computation or minimum computation. Okay, so this is, the conclusion for this talk. We showed that if we first code the data and then do the computation, that the coding should be like, such that it works the best for our channel, then we can save both computation and communication and achieve minimum communication and computation at the same time. And so, as you can see, there are a lot of problems here. Okay, so in every direction there are problems. So, how about other channels, other functions, other scenarios? You can imagine there are a lot of problems. So here in this lecture, I try to cover the role of coded computation in three different problems. One of them was map reduced. The other one was to deal with stragglers. And here, like to achieve minimum communication and computation. This field is growing. It's at the very beginning, and every few weeks you see a new paper, very nice paper. I just covered a few of our papers, but there are a lot. If you want to know more about it, there was a good, tutorial in ISIT, and the slides are available. You can see it, like Kadambe and Pulkit Rover. They had a nice workshop on coding for computation. You can see their slides too. Okay? And I think this is a nice field to jump in and think about. Thank you.
Questions from the audience?
So I have a question regarding your matrix computation.
Oh, okay.
So you're using a read Solomon code?
The result is in Solomon, yes.
Right. So is there a result that says you cannot use product codes? You need a product MDS code.
You need something that when they multiply together, they become MDS code.
Because I think if you could find the product code, you could encode the matrices separately, whereas in your case you have to encode them jointly. Because you need the coefficient of your Solomon code to combine the two matrices.
I don't know, I have to check. So you're saying that product code can do this for us?
Well, that's thing, I don't know. I mean, usually the product of two MDS code is not MDS.
Yes.
But if you can find one, you could also simplify the calculation.
This is exactly that. See, if you look at it here, the code that we have, one of them is not. Most of them are kind of coded in like an MDS type of coding. Okay, it's not exactly MDS, but the way that we are doing it. The first one is definitely with Solomon. Okay, the first one is definitely with Solomon. The second one is not exactly with Solomon because we are jumping by two. You can say it's like type of Solomon code. When they multiply together, it becomes exactly with Solomon. Because this one is with Solomon. Yes? I agree. Here, if you had b0 plus b1x, it was Solomon. That's b0 plus b1x squared.
Wait, that's still okay, right? Because x squared could be a base element.
True, yes, but you have, you can think exactly. You can call it alpha, and then this one also is with Solomon. But these two has to be designed with respect to each other such that the result also becomes Solomon. If you don't do it, it's not. The result is not.
I think the key feature that's probably will not be captured by code is that you want that in the next step, each server can get a small message and compute just that small part that it's producing. Right? And that's not true. In general, in the code, each coordinate will depend on many things, but you in the next step will just send a very small message to your server.
Exactly. You're sending exactly this combination information. Yes.
This is a short message. If you use some code where you're going to have to send a huge message, you defeated the whole purpose.
Exactly. Yes. Yeah. If you ignore this fact, then you could do. There are a lot of approaches to do that. So here, the computation that we do at each node and the storage that we have in each node is exactly as before. Still, we can manage to have the result being this.
Other questions or comments? Just to follow up on Madhi's question about real matrices and real read-something code. I mean, these exist, but the condition number keeps getting worse as the dimensions of problem increase. So, but I guess you don't have like a humongous number of servers that you can.
I agree. So you're saying that when we have excess or larger power of x, then things become very bad. Yes. Numerically, theoretically it's okay. Numerically, you will have problems.
All right, let's thank the speaker again. As always, we'd like to present our speaker with a souvenir. I think we need like a nice stage photograph. Is there a slide you'd like to highlight? Which?
Yeah, let's do this one. Good? Okay. Okay, thank you very much. Thank you.
So yeah, we